بسم الله الرحمن الرحيم، والصلاة وسلامي على سيدي ومولاي محمد بن عبد الله وعلى آله وصحبه أجمعين. محمد بن عبد الله الذي أمره الله سبحانه وتعالى بأن اقرأ باسم ربك الذي خلق الإنسان من علق، اقرأ وربك الأكرم الذي علم بالقلم، علم الإنسان ما لم يعلم. والذي قال الله سبحانه وتعالى أيضا في محكم آياته وأمر المسلمين بالإيمان بمحمد صلى الله عليه وسلم والإيمان بجميع الرسل والأنبياء، كما قال آمن الرسول بما أنزل إليه من ربه والمؤمنون.
Introduce myself. Yes, my name is Jeffrey Oakes, and I'm a advanced professor at the University of Indianapolis in the United States. And I've been studying medieval Islamic mathematics for the past perhaps 15 years. And one of my interests, especially, of course, Khwarizmi.
I'm John Crossley.
الرسول محمد صلى الله عليه وسلم قال عنه الله سبحانه وتعالى أو قال في محكم آياته آمن الرسول بما أنزل إليه من ربه والمؤمنون كل آمن بالله وملائكته وكتبه ورسله لا نفرق بين أحد من رسله. طبعا هذه أنا كنت بالأمس من يومين كنت في بروكسل، وكان عندي ورقة عن التسامح في الإسلام والحديث عن نبذ العنف والإرهاب وما إلى ذلك، فكنت أتحدث في هذه القضية بأن الإسلام دائما يأمر أتباعه بالإيمان بجميع الرسل والأنبياء. أحييكم جميعا أيها الإخوة. بسم الله الرحمن الرحيم، والصلاة والسلام على سيدنا محمد وعلى آله وصحبه أجمعين. نعيد الكلام مرة أخرى بصلاتنا على سيدنا محمد وفي الصلاة عليه بركة. الرسول كما قال الله سبحانه وتعالى آمن الرسول بما أنزل إليه من ربه والمؤمنون كل آمن بالله وملائكته وكتبه ورسله لا نفرق بين أحد من رسله. المهم قصة حضوري للمؤتمر ليس لها هنا يعني مجال، ولكن الآن سنتحدث عن أحد الأئمة أو العلماء المسمى بمحمد بن موسى الخوارزمي المتوفى 232 للهجرة، وجدير بمركز يعنى بالحضارة الإسلامية، وهو مركز محمد بن حمد الثاني لإسهامات المسلمين في الحضارة وتراث الحضارة الإسلامية وتأثير هذه الحضارة على بقية الحضارات. جدير بهذا المركز أن يلقي الضوء بين الحين والحين على إحدى الشخصيات الإسلامية العلمية التي تركت أثر في علمها وفي إبداعها وفي اكتشاف كثير من العلوم حقيقة في كثير من المجالات لتهتدي به البشرية. هم لم يكتشفوا تلك العلوم فقط لأنفسهم أو للمسلمين، إنما هم أرادوا بها يعني خير البشرية بصفة عامة. من هنا سيكون حديثنا في هذه الجلسة عن الإسهامات العلمية لمحمد بن موسى الخوارزمي، وهو يكنى بالخوارزمي نسبة إلى بلد ولد فيها في جمهورية أوزبكستان، ولكنه انتقل إلى بغداد مدينة الحضارة الإسلامية. يعني ندعو الله سبحانه وتعالى لبغداد ولأهل بغداد وللعراق ولكل الدول العربية المبتلى أن يرفع الله سبحانه وتعالى عنها البلاء ويعيدها عودا حميدا. هو الخوارزمي يعتبر من أوائل علماء الرياضيات من المسلمين، وقد ترك الكثير من المؤلفات في علوم الفلك والجغرافيا. ولنبوغ الخوارزمي في علوم الرياضيات أحببنا أن نعطي المتخصصين والبارعين في هذا العلم فرصة الحديث في هذا المجال، ونعطي أنفسنا فرصة الاستمتاع والاستماع إليهم بحديثهم عن هذا العالم الجليل. سنبدأ بالدكتورة تماضر خليفة سلطان صباح العسيري من دولة قطر، وهي أستاذ مساعد بقسم الرياضيات والإحصاء والفيزياء بكلية الآداب والعلوم في جامعة قطر. انضمت إلى هيئة التدريس بالجامعة بعد تخرجها بتميز من جامعة قطر، وقد حصلت على درجة الماجستير في الرياضيات الحديثة التطبيقية من جامعة شفيلد هالام في بريطانيا سنة 2001، كما حصلت على دبلوم عالم في التعليم العالي أثناء دراستها للدكتوراه في سنة 2005، وقد منحت شهادة الدكتوراه في الرياضيات تخصص تشفير سنة 2009 من جامعة لندن كلية رويال هولوي أو هولي. تفضل الدكتورة، وبعد ذلك سنبدأ مع الأخوة الكرام.
السلام عليكم ورحمة الله وبركاته. أنا الحمد لله نستعين ونستغفره ونستهديه ونعوذ بالله من شرور أنفسنا وسيئات أعمالنا، من يهدي الله فلا مضل له ومن يضلل فلا هادي له، وأشهد أن لا إله إلا الله وحده لا شريك له، وأشهد أن محمدا عبده ورسوله. أما بعد. I was asked if I can give a talk on Khwarizmi. They said a 15-minute talk about Khwarizmi. So I thought, okay, yes, I can do this. And then they sent me who the other speakers are. And then I read into what the research is. And then I got scared a little bit because it's different from my field. I was going to give a general talk about Khwarizmi, and then I saw that their research is so extensive and detailed. So I thought, oh, that's going to be hard. But then I thought, it's okay. I just make my speak general and speaking to the general public, and I can learn from them and they can correct me if I make mistakes in this field. So I'm going to speak today about an overview of our Khwarizmi contribution in different fields. So I'm going to go away a little bit from the maths because some of the other speakers are already going to talk about the algebra part of this field. So to begin with, Al-Khwarizmi, there is not much about his biography except what Dr. Asha already said, that he came from Khwarizm. He was famous because he got called to Baghdad when it was the time of Khalifa al-Ma'mun. He had Bayt al-Hikmah there, and he was head of Bayt al-Hikmah for a while, and he got encouraged by that, as well as many other scientists at that time. And this is why we have the Islamic contribution in different fields from that era. So I'm going to start with some. So there are many fields that he went into, like scientists in that time. They are usually not very restricted like we are. We are mathematician, cryptography, that's it. You just do one thing. You just concentrate on one thing. Or if you do a PhD thesis, and then you have to go back and do the same and the same and the same as your PhD thesis. But it's nice to see different fields and see different things. They're all related, of course. They're not so far away from each other. But still, there are different applications of the same field. So these are the words from Philip Hitti, talking about Al-Khwarizmi. He influenced mathematical thought to a great extent than any other medieval writer. So this was a historian, Philip Hitti, talking about Al-Khwarizmi. First of all, we all know, everyone knows, when you hear Al-Khwarizmi, the word directly goes to algorithm, Khwarizm, where it comes from, and you know he is the person who based the science of algebra as we know now. And he started with, he founded the analysis of algebra and how it was distinct from geometry, as well as solving equations of second degree, first degree, and using geometry, as well as using different methods of algebra. Also, he has some contributions in geometry, even in his most famous book, Al-Jabr wal-Muqabala. There is a part where he's speaking about triangles, areas, and surfaces, and circles, as well as definition for pi, and evaluation of pi that is more accurate than it was before. This is just one page of his book, Al-Jabr wal-Muqabala. And I will leave the rest of the algebra to my colleague there. The other thing that he contributed to is what we call Arabic numerals or Indo-Arabic numerals, because the Arabs did not invent them. They came from India, but they were crossed over from the Arabs to the Western world, and they used the method of calculation using these numerals, which made it a lot easier for all the calculations and so on. Using this method is when you have the numbers and like digits, and then the tenths and the hundredth and thousand, makes it a lot easier than using the old Roman numerals for counting and calculations. So this is one example I got from a paper that is mentioned in one of Khwarizmi's work. It's not exactly the same, but it's the method. And there's the same, similar method for multiplication and division and so on. But this is the simplest one, is subtraction. So how it's done, you have to read it from the right side. So starting subtracting 3,211 from 6,422. So you write them exactly under each other, and then you start with the thousands first, and you write the result of subtracting the thousand, and you remove the thousand from the lower one. And the same, when you remove the hundreds, it becomes 3,222, and then you just have 11 left, and then you remove one of the tens, and you have 3,212, and then you remove one, and you get 3,211. So it's basically the same method that we use now, but we just write them differently, but it just makes it a lot easier for the calculations when we use these digits as numerals. Another contribution was in fiqh and inheritance. There were some things about mu'amalat or financial deals, buying and selling in Islamic ways, and so there are in some of his books, as well as in the same book, Al-Jabr wal-Muqabala. At the end of his book, he has some applications of the algebra in the inheritance laws. So he applies the inheritance laws and uses the calculations to find them. When I was undergraduate student, I was studying mathematics. I went and took a course in inheritance because it was easy for me. And every other student was struggling because it was fractions, dividing, and addition, and for me it was, we're doing nothing. So this was just an example. I don't want to go into the details, but this is one example of one question or the example of the inheritance. Like when you have a lady who passed away, and she had a husband, one son, and 3 daughters, and she has a will of 1/8 and 1/7 of all her money. So you'd have to add the 1/7 and 1/8 and reduce it, and then you have to use the fractions to see how many parts you need. Like this, it's a little bit hard to follow if you don't see one by one, but sometimes they write it in a table like this, so it makes it easier for the calculation. Because you have the 1/4, and then you have here 3 parts, so you have 1, 2, 3, and then you know how many parts you're dividing to. And then he has many contributions in astronomy as well. So he had a book that was Zij Hind. So he was combining Persian and Indian known things in astronomy, and he made the astronomical tables and trigonometric tables as well. So this goes back to the math part of the trigonometric, which was sine, cosine tables, and they were translated into Latin in 12th century. They contained the first Muslim tables, and not only sine function but also tangent functions. And it was studied further also by another mathematician or astronomer. He was called Muslim al-Majriti, where he took the works of Khwarizmi and extended a little bit to the tangent as well. And also he had collaborated with, for degree measurements by Al-Ma'mun. They were trying to find the volume and circumference of the earth at that time. He had 2 books on the astrolabe, which is the measuring tool that was used to measure distances using the stars. So he had 2 books on mastering those, and also he had some contribution in using the sundials, and mostly they were used for timing prayer times and knowing the time for prayers. And for the direction also of the Qibla, they also used some methods using the astrolabe and so on. So it was all applications of his science to the other fields as well. And then he has some things in geography. He has a book called Kitab al-Ard. He organized the works of Ptolemy and added to it some values of latitude and longitude. When I saw this book, I have a copy of it here. I got it from Qatar University Library. It's amazing when you see how you have all these numbers of latitude and longitude. And if you think this was 7th century, so really long time ago. And when we study it now, we think this is some new science, but it's not. It's been there for a long time. They were working on drawing a map of the world for Khalifa al-Ma'mun. Unfortunately, that map has been lost, but there are some scientists who try to redraw it using the information for the latitude and longitude points that are in his book. This is one of the maps that were in the book, and this is a map of, first of all, I thought it was, you know what, because the kinds of map that I'm used to see are different. So this is the map of the Nile River. The Nile River. So you can see on top there is Iskandariya, and then there is in the middle there, it says Aswan, Aswan, yes, and then I think this is Lake Victoria, as we know now. That is the base, the start of the Nile River. Some of his books, I don't know if I want, I wasn't sure that I'm not going to read this, it's just too many. Unfortunately, many of them are lost as the original books. But we have some of them survived by translation from other scientists when they reached the Western world in the 12th century. So he had many books in the fields that I mentioned, and there are other contributions as well. So that's all I have today. Thank you very much.
شكرا جزيلا دكتور تماضر. والله عجبتني فكرة المواريث، يعني أنا ما أعرف يعني هل يعني الفقهاء أو يعني قوانين الأحوال الشخصية تأخذ بها يعني بالتقسيم. طبعا هو التقسيم 100% يعني عن طريق القرآن والسنة، ولكن قصدي سهولة أو يسر تطبيق هذا التقسيم. أتصور مهم جدا الأخذ به يعني من عالم في الرياضيات أيضا يعني، وكما قلتي يعني بأن بالنسبة لك أصبح سهل بالنسبة للمواريث، وهذا أتصور شيء متميز يفترض أن يدرس بالنسبة للطلبة والطالبات، مهم جدا وبخاصة في مقررات المواريث يعني. شكرا جزيلا دكتورة. الآن افتحوا لنا النور لو سمحتوا. الأستاذ الدكتور جيفري أوكاس من أمريكا، أستاذ الرياضيات شعبة الرياضيات وعلوم الحاسوب في جامعة إنديانا بوليس في أمريكا، حصل على شهادة الدكتوراه في الرياضيات الهندسة التفاضلية من جامعة روشستر بنيويورك. له ورقتين هامتين جدا بعنوان الهندسة والإثبات في الجبر والسلسلة من المشاكل في الجبر للخوارزمي. تفضل دكتور جيفري.
So I need to find, hold on just a second. Okay, my main area of research is history of medieval Arabic algebra, so I decided to focus my talk on Al-Khwarizmi's contributions to that area. In fact, if I wanted to talk about his contributions in general, my talk would last 3 or 4 hours long, and it still would be incomplete. So let me, there are really two phases to Al-Khwarizmi's career in algebra. One is within the Arabic world, where he really set the stage for how algebra was to be conducted. And his influence it was a profound influence that lasted through the entire period of Arabic algebra. But then it was reborn again when his book was translated into Latin in the Middle Ages, and that set the stage for his profound influence on the development of algebra in Europe as well. So I just show in this slide on the left a page from the Berlin manuscript of his algebra book, just to show you how it looks. And on the right-hand side is a page from a manuscript of Gerardo Cremona's Latin translation, which was made in the year 1187. So, and you'll notice, of course, that the algebra in both cases is entirely rhetorical. They wrote even the numbers out in words, and there's a reason for that, but I probably won't have time to get into it. Anyway, so just as an outline for my talk, I'm going to talk a little bit about the cultural background to the transmission of knowledge around the time of Al-Khwarizmi and beforehand, which will set the stage for me describing what Al-Khwarizmi's own contributions were to algebra. And then I'm going to talk about his influence on Arabic algebra, Latin algebra, Italian algebra, and so on, down the line. So, okay, now many of you know about the translation movement, which occupied the first, say, 2.5 centuries of Abbasid rule. And this was actually the major part of a larger gathering of knowledge that included not just books translated from Greek into Arabic and books on the Indian arithmetic and astronomy, but also people were gathering together books that had been transmitted orally. And I'm going to name a couple of these too. Part of what made the translation movement possible was the introduction of paper to the Islamic world around the year 750, which anyway, so regarding oral knowledge circulating in the Middle East, many of you may be familiar with the Arabic folk astronomy. This was a different tradition from what we find in Ptolemy and from the Greek tradition. And I think the first person to write a book on that in Arabic was Thabit ibn Qurra in the late 9th century. We also have mensuration, or practical geometry. This is the geometry that people who do surveying and architecture use, and this is also distinct from the Greek tradition. In fact, Al-Khwarizmi's algebra book is the earliest earliest book we have in Arabic that shows a treatment of mensuration, as we've already heard. So algebra itself had been practiced before, but it was kind of a disorganized technique of practical problem solving along with other techniques. And they were both associated with finger reckoning. So finger reckoning was a method of mental calculation where you store intermediate results on your fingers, because one could store the numbers from 1 through 999 in your fingers. And this is how most calculation was done by merchants and even government secretaries at the time. So books on these topics, these are kind of the oral topics that were written down first in the 9th century, and were eventually mixed in with the the foreign texts. So, like I said, algebra did exist before Al-Khwarizmi's time. We have no idea who actually invented the technique. It definitely existed, and I should back up just for a second. When I speak of algebra, I'm talking about the practical technique of numerical problem solving, where an unknown is given a name, and an equation is formed from that name through operations on the named unknown. This is distinct from other methods of problem solving that were current at the time, like double false position, single false position. I don't know how many of you are familiar with other techniques of problem solving. And we find this kind of algebra already in Diophantus in Greece, but he didn't invent algebra either. He did pretty much what the same thing Al-Khwarizmi did. He took something that had been practiced by practitioners, by people doing calculations in their jobs, and elevated to how should I say, to a textual tradition. But Diophantus in the end did not have the influence Al-Khwarizmi did. But I have to mention Diophantus because he does creep into the story along the line as we go through the years, because he was translated into Arabic, and he was also later on translated into European languages. In fact, when his book was translated into Arabic, it was called the Book of Algebra. Arabic algebraists recognized Diophantus as having been an algebraist. So the bottom line is we do not know who invented this technique, but Al-Khwarizmi is the scientist who gave it its form. Al-Khwarizmi is the one who took this loose collection of techniques and sort of, you could almost say, turn it into a science in some sense. And this is how it's attributed in Abu Kamil in the late 9th century. He says Al-Khwarizmi is the person who, I can't remember the wording now, but I'll tell you later if you ask me. So anyway, I'm listing here the main books Al-Khwarizmi wrote, and just to give you an indication that the three that I show in red are the most important books that he wrote, because these are the ones that were translated and commented on for centuries, not only in Arabic, but also later in Latin and European languages. So the Book of Algebra is one of these. The Book of Indian Reckoning, we're going to hear about that one in a minute. And of course, his book on astronomical tables was translated and adapted and mixed with other books, and pieces of it are found in texts extending many, many centuries past his own time. And I put little bullet points on the left for the books that survive in at least some form today. Most of the books are lost, unfortunately. Now, in order to explain the transmission of certain of Al-Khwarizmi's ideas, I have to give you some idea of the outline of how his book is organized. So, as you can see here, I've done this for the Oxford manuscript of the text. So, just to show you size-wise how things go. So we have an introduction, followed by some rules/theory. These are the rules of algebra that one needs to know in order to solve problems. Then Al-Khwarizmi gives 40 worked out problems. So he'll give you an arithmetic problem. Here's a solution by algebra, one after the other. Now after that, this is really what we call the algebra proper, because the parts that come after are kind of tacked on the end as part of this practical treatise. So we have a brief section on the rule of three, which was another technique of problem solving, and the chapter on mensuration, followed by a long section on solving inheritance problems by algebra. To our knowledge, he's the first person to ever apply algebra to inheritance problems. So, and I'm going to talk mainly about the first part, the algebra proper, which consists of the rules followed by the 40 worked out problems. And I'm afraid I might be going over my time, but I'll try to cut myself off if I do, okay? So according to the rules here, according to Al-Khwarizmi, there are 6 kinds of simplified equation of degree 1 and 2. And 3 of these equations are simple, they only have 2 terms, and 3 of them are composite, so they have 3 terms each. The simple equations are very easy to solve because one just divides by the coefficient of the highest power, but the other equations are not trivial to solve. And let me see how I go here. Yeah, so Al-Khwarizmi actually introduced the geometric proofs for these rules, and I'm going to show you a picture of one of them in a second. So, and this is just a preface right here. So for the section on rules where he's describing these equations, what he does is he gives the names of the powers and he solves the 6 equations, and then he gives the proofs to the solutions to the composite equation. And what I've highlighted in red will appear in many medieval Latin and Italian books later on in very near translation or slight adaptation without any attribution to Al-Khwarizmi. The rest of it are more rules of algebra that didn't last quite as long in the textual tradition. So here are 2 pages from the Oxford manuscript of Al-Khwarizmi's algebra, and this one shows 2 of the geometric proofs for the rules for solving equations at the bottom, as you can see. Now the one proof I want to show you, which is very characteristic of Al-Khwarizmi, I don't have a nice scan of. All I have is this, which comes from a Spanish edition where they've actually traced in the red by hand to make the addition. But what you're going to see is that in the top diagram we have this sort of 3x3 rectangular grid. I'm not going to explain the details of this proof, but it's a very, very curious proof that no one would come up with independently. So it's kind of like a fingerprint. When we see that proof, we know it came from Al-Khwarizmi, and it does pop up occasionally in later treatises. So, yes, we could do a seminar once every week. I could explain where all of that comes from. And the other part that gets transmitted in many different authors beyond the translations of Al-Khwarizmi's work in itself are the worked out problems. Many of the worked out problems are copied by other algebraists later on. And this is I've just shown you an example here of a worked out problem. In the blank area, it's supposed to say, al-masala, it's supposed to say the 5th problem, but the person never came to write the red ink in. Anyway, the problem begins 10, ashara, you divided it into 2 parts such that, and then the problem goes on from there. So this is how a worked out problem looks in Arabic algebra. We have Yago here for equals. I don't know if you can, I can't point to it now because it's too large. But anyway, so you can look at that later if you want. For other talks where my audience is mainly English speaking, I actually have an English translation, but we won't need to dwell on that. So anyway, so the question is, what was original in Al-Khwarizmi? I claim that, and I've argued for this before, the classification of the 6 equations, that is Al-Khwarizmi's idea. The proofs of the rules. He is the one who decided these rules need proofs, and he supplied them. And the first 6 of the 40 problems are definitely his. The rest of the problems are clearly taken from an oral tradition. In fact, some of them are not even solved by algebra at all. They're kind of disorganized and they're not worded very precisely, but the first 6 problems are worded very precisely, and they really appear to be Al-Khwarizmi's own improvements on the tradition he was inheriting. In fact, the way he phrases these problems later became the standard for Arabic problems solved by algebra from his time until the end of medieval Arabic algebra. So what was not original in Al-Khwarizmi? The algebraists certainly knew how to solve the composite equations, and just a general method of naming unknowns. That's what we figure actually existed before Al-Khwarizmi's time. So in a large sense, you can say that Al-Khwarizmi invented or even reinvented algebra. Diophantus did something similar, but it's not quite the same, and you can see Al-Khwarizmi's own mark on the art here. Okay, so let's talk about Al-Khwarizmi's influence on Arabic algebra. So, yeah, so the algebra books that came after him are generally organized in exactly the same way Al-Khwarizmi did it, which is to say that they will have a section of rules in the beginning, followed by the worked out problems in the end. And among the rules, there will be a classification of the equations into 6 types, and very often they have geometric proofs. Later on, they'll actually have arithmetical proofs, or sometimes no proofs at all, depending on the audience of the intended book. So, but this form here, you don't see this in Diophantus, and you don't see this in say, there's actually a kind of algebra that was worked in India around the time of the 6th century by Brahmagupta and others, and that algebra doesn't seem to have any relationship to what Al-Khwarizmi was doing. So Al-Khwarizmi's, the basic form of the book is Al-Khwarizmi's idea. And Al-Khwarizmi was a major influence on Abu Kamil, who worked in the late 9th century in Egypt. Al-Khwarizmi's book on algebra is an expanded version of Al-Khwarizmi's book, and it can almost be called a commentary. And Abu Kamil's book almost rivals Al-Khwarizmi as an influence in the centuries that followed. But since Al-Khwarizmi derives from since Abu Kamil derives from Al-Khwarizmi, we can almost say that really we're looking at Al-Khwarizmi when we read Abu Kamil. So, and here I list some very important works by medieval Arabic algebraists who were influenced by both Al-Khwarizmi and Abu Kamil, such as Al-Khwarizmi, who's made a number of innovations, including the arithmetical treatment of polynomials, which had never been done before. I don't write that here, but here I write down what he actually took from our previous authors. His book is structured like Al-Khwarizmi's book. He gives the same classification of equations, and he takes many, many problems from Abu Kamil's book. Now, Abu Kamil took many problems from Al-Khwarizmi's book, but they're not the same problems, but it's the same kind of idea. Al-Khayyam, Umar al-Khayyam, of course, is extremely famous as a medieval Muslim mathematician, but he was a theoretical geometer working in the Greek tradition and staying faithful to Aristotle and his philosophical outlook. But actually, Al-Khwarizmi's influence can be seen there too. I showed you that one diagram from the one proof that looks like a 3x3 grid. He has that proof in his book to cover that particular type of equation. So Al-Khwarizmi even has an influence there. And I've named two other minor algebraists who are also influenced by both Al-Khwarizmi and Abu Kamil. One is Ali al-Sulami, and the other is Ibn Badr. Ali al-Sulami's book exists in a manuscript that's in the Vatican, and it has not been published yet. But again, and Ibn Badr's book has been published, but I think it was written in Spain sometime a little bit later than that. But in both of these books, we find the same structure, and we find problems that are taken from both Al-Khwarizmi and Abu Kamil. So these two authors were influenced by both. And these are not the only ones. There are many, many authors who were influenced by Al-Khwarizmi and Abu Kamil. I'm just listing some of them. Now, getting back to Al-Khwarizmi's book itself, there are several people who wrote commentaries on it. So there were four people who wrote commentaries on Al-Khwarizmi's book, and the last person listed wrote a commentary on the commentary. So, and I should say something about the first three authors here. Sinan ibn al-Fath wrote, he not only wrote a commentary on Al-Khwarizmi's algebra, but he also wrote books on exactly the topics that Al-Khwarizmi worked on. One could almost say that he based his whole research project on Al-Khwarizmi. And then we have Saidanani, also wrote a commentary not just on the algebra, but also on another book of Al-Khwarizmi's, the one on business arithmetic. Abu al-Wafa is quite famous. He wrote commentaries on the books of algebra by Al-Khwarizmi, Hipparchus, and Diophantus. All three of them. He covered all three of these books. Muhammad al-Khuzai, I wish I could spend more time on his commentary because it has some interesting stories to it. But he wrote about the oral tradition from which Al-Khwarizmi drew. And the last person wrote a commentary on I can't pronounce his name, Al-Khuzai. I apologize for this. On his commentary. So there was a tradition of commenting on Al-Khwarizmi's book on algebra as well. Unfortunately, all the commentaries except the fourth one are lost. We only know their titles because of Ibn al-Nadim's catalog. Okay, now I'm going to pass to medieval Latin. In the 12th century in Spain, there were a number of Christian scholars who wanted to emulate the more powerful and more knowledgeable Muslims, and so they took it upon themselves to translate many of the scientific treatises into Latin. And Al-Khwarizmi's algebra was translated 3 times. It was translated first by Robert of Chester in the year 1145, then by Gerard of Cremona. I show a page here from Gerard's. This is the same photo I showed you before. And it was also translated a 3rd time. It's actually more of an adaptation than a translation since he leaves out so much stuff, but by Guglielmo de Lunis, an Italian person. So we have 3 different translations of the same work, which is quite remarkable. And also in medieval Latin, Abu Kamil's book, the long book on algebra that was almost a commentary on Al-Khwarizmi, that was also translated into Latin in the 12th century. That still survives and has been edited. Fibonacci, who's rather famously known for having written his Liber Abaci, which is a huge compendium. The English translation is over 600 pages long, and it derives all of its material from Muslim sources. In Fibonacci's chapter on algebra, you can see very strongly the influence of Abu Kamil, but also the influence of Al-Khwarizmi. And then there's an interesting person here who is less known. Jean de Meur worked in France and wrote a Liber Quadrapartitum in 1343. And in it, he includes a Latin translation or adaptation of almost all of the first part of Al-Khwarizmi's book. It's clearly taken from Al-Khwarizmi's book. In fact, I'm showing you here a page from the critical edition, and you can see the diagram at the bottom of the page is the same diagram we see in Al-Khwarizmi. So even though he never names Al-Khwarizmi, he essentially presents Al-Khwarizmi's algebra in his book. And his book actually was read by quite a number of people later on, too. So we have the Al-Khwarizmi living on without his name attached to his work for many centuries here. And then we pass to medieval Latin. What's interesting is that in Italy, the merchants in Italy in the 1200s, 1300s, and 1400s were trading with the Muslims in the Mediterranean, and that, of course, is where they learned basically all of their mathematics. And they began teaching this mathematics to their own, to the children of merchants in central and northern Italy. And there are many, many textbooks that survive in manuscript form from this period. And here's I'll show you an illustration from one of the later textbooks showing the abacus master teaching the children the arithmetic that's needed for conducting trade in the Mediterranean. So it's very nice to have some illustrations once in a while. But these books are structured differently from Al-Khwarizmi's book. We really don't know the path by which these people learned the algebra from the Muslim sources. They'll generally list 50 or 60 or even more different kinds of equations up to 4th, 5th, and 6th degree. And it's a far cry from Al-Khwarizmi's 6 types. So influence of Al-Khwarizmi is even more pronounced when it does occur. And it occurs in the following forms. Al-Khwarizmi's Latin translations, 2 of them, were translated into Italian. So we have Italian versions of the Latin versions of Al-Khwarizmi's Arabic original. Also, Fibonacci's chapter on algebra was translated into Italian. We have a manuscript there. So Al-Khwarizmi's algebra survives in translated form in that respect. Now, what's curious is that Al-Khwarizmi's classification of the 6 equations with the proofs, the part that I highlighted in red many slides ago, are reproduced, sometimes with modifications, in 4 different of these abacus texts. One of them written in actually it's supposed to be 1344, that's a typographical mistake. Maestro Dardi's Aliabra Argiva, you can see the bad transliteration of algebra twice. It was written in 1344. Benedetto da Firenze wrote a book called The Rule of Algebra around the year 1460. We have anonymous texts from the same time, and Raffaello Canacci wrote a book around 1495. All of these books give almost the entire introduction of Al-Khwarizmi's book kind of in modified form of a translation from the Latin. So unlike in the Arabic, the Arabic authors never copied Al-Khwarizmi like the medieval authors did. The Arabic authors would look at Al-Khwarizmi and come up with some new way of saying what they thought would be a better way of doing it. But in Italian and in Latin too, they kind of stuck to certain patterns and didn't diverge from them. Now let me see, how am I doing for time? Perhaps I'm running over. Well, whatever, I'm just going to talk. Okay, so anyway, so what really curious, this is going to come up in a minute. Benedetto da Firenze's book begins like this. Here begins the text of Arabic algebra. So they knew it was from Arabic, called the Rule of Jebr. Jebr is just a bad transliteration of algebra, which we call algebra. And this is an Italian word, is algebra. This rule of algebra. So what he writes here, he writes the same thing twice, but with 2 different spellings. But Italian had no standard for spelling at all. People just wrote phonetically. So this rule of Jebr was called in Italian Regola del Jebr. And this caused a misunderstanding later on, which is rather interesting. So I'll get to that in a minute. I just had to set the stage for that now. But first I want to talk about Al-Khwarizmi in Germany. And I still have to piece all of this together. Latin translations of Al-Khwarizmi were owned or read by several important German mathematicians from the 1400s to the early 1600s. Regiomontanus is a famous mathematician who's going to come up in a minute. He's a famous mathematician and astronomer from Germany. Johann Widman is the person who introduced the plus and minus signs to mathematics. He had a copy of Al-Khwarizmi's algebra in the late 1400s. Adam Rice he also wrote his own books, and Schubel is actually a very famous German mathematician who also owned a copy of Al-Khwarizmi's book. And Adrian van Roomen may have been Dutch, but he was working in Germany when he acquired his copy of Al-Khwarizmi's algebra. So even if these people didn't write texts which explicitly reflect Al-Khwarizmi, they all had read Al-Khwarizmi, and of course they knew it was Al-Khwarizmi because they were dealing with translations that said so. So this is something I have to try to eventually piece together with what follows. Oh yeah, here's where Diophantus comes in again, because Regiomontanus in the early 1460s discovered a manuscript of Diophantus's book in the Vatican Library. And he recognized it as being algebra because we know this because in a letter to an Italian colleague, he writes that Diophantus and Al-Khwarizmi both list the names of the unknown powers, and then they work with these unnamed. So he's actually corrected in this little assessment here. And he made a public lecture about the discovery of Diophantus in Padua, which has been commented on many times by historians. He writes, "But no one up to now has translated from Greek into Latin Diophantus' 13 most subtle books, in which the flower of all arithmetic lies hidden, namely the art of the re and census." Re and census are translations of Arabic terms, by the way, which today they call by the Arabic name algebra. So he's recognizing something common here, and he doesn't have a Eurocentric viewpoint because this lecture was a lecture on an Arabic astronomer. In other parts of this, he cites many famous Arabic mathematicians and astronomers. He's just recognizing that Diophantus belongs in this picture somehow. He's not sure how because he's not really read the text. So that's going to come up a little bit in a bit too. So Al-Khwarizmi also left his mark on early printed books in Europe in the 16th century. His influence extends this far. But unfortunately, it's only just his name. Where we see in the medieval Italian books, we find his work, his text, his organization, his proofs included in books, but without his name attached to it. Now we find his name, but without any of his work. So it's kind of like a backwards situation here. So we find many books written in Latin, Italian, French, German, Spanish, and Dutch, all citing that algebra comes from Muhammad ibn Musa, the Arab. But there are two other names that appear in these books as well. One of them is Jeber, which of course really should just mean algebra and not the name of a person, and Diophantus, because of Regiomontanus' announcement. So Francesco Galligai made an error in his 1521 practical arithmetic book where he cites Benedetto da Firenze, but he mistakes Jeber to mean the name of a person, to be the name of the person who developed algebra. I'm sure you heard the medieval, the Italian here. Benedetto says the rule of algebra. I'm not going to read it to you. Anyway, so you can see what he is. He makes a mistake. He misunderstands what Benedetto says. And now Jeber becomes a person. So here's what we have. We have three people who are declared to be inventors or developers of algebra in 16th century European books. We have Diophantus, we have Al-Khwarizmi, and we have this fictitious Jeber, who was later, by Michael Stiefel, identified with Jabir ibn Aflah, who was an astronomer in the western part of the Islamic world, and whose name had been transliterated as Jeber. So this is just a mistake of Stiefel's and of Galigai's. So we have two real people and one imaginary person. So, but Cardano, of course, Cardano is the famous person who first published a book with solutions to cubic equations. Cardano writes, "This art originated with Muhammad, son of Musa the Arab." And that phrasing matches the medieval Latin translation. So almost certainly Cardano also had access to the medieval Latin translations. And for Diophantus, people always cite Regiomontanus' little announcement in his lecture in the 1460s. So what I did here, just for fun, is I wrote down a table of a bunch of mathematicians from the middle to late 1500s and who they cite as being an inventor or developer of algebra. And it's kind of split between all three of them. Some people mention all three, like Jacques Pelletier in 1554 mentions Diophantus, Al-Khwarizmi, and Jeber. Not as so much as inventors, but as people who developed the art. So in this sense, Al-Khwarizmi's name survives attached to algebra down to the end of the 1500s, and actually beyond that as well. There's no way I would have time to explain how it developed from being cited in algebra books to actually becoming the person historians are investigating into that we have today. So my summary, let me just summarize everything here. So In Arabic, we find Al-Khwarizmi determined the structure of later books. He gave organization to algebra that it didn't really have before. He really defined algebra as a body, as a work to be studied. And the fact that he wrote it down in a book was the first step towards later scientific developments. And he also began an interesting tradition of geometric proofs. In Latin, we saw that Al-Khwarizmi's book is what introduced algebra to Europe, and it served as a source for several centuries, actually not 4 centuries in Latin, or actually I guess it would. 4 centuries in Latin translation, and in Italian we find, of course, a major impact. And in 16th century Europe, he remained nothing but a name for algebraists. Of course, the algebraists in the 16th century were not historians; they were just algebraists, and they just cited his name in the beginning. So that's how the trail of Al-Khwarizmi's influence progresses from his own time down to 16th century Europe. Of course, in 16th century Muslim countries, his influence was still being felt, but his book was not being copied or read anymore. So that's it.
شكرا جزيلا. حقيقة استمتعنا جدا بهذه المحاضرة، ويعني أوضح لنا الأخ الكريم الأستاذ الدكتور جيفري أوكاس يعني كيف تأثر أو كيف أثرت كتب الخوارزمي في معرفة المسلمين كما تحدث، وفي الرياضيات في الغرب. وحقيقة استمتعت لأن أنا بالنسبة لي ممكن لأني غير متخصصة، فأشعر بأن كل معلومة قالها بالنسبة لي مكسب، وعرفت يعني أثر فيا، وعرفت تأثير الخوارزمي بهذه الصورة. شكرا جزيلا. الأخ الكريم الأستاذ الدكتور جون كروسلي من استراليا، رئيس قسم الرياضيات وعلوم الحاسوب في كلية كلايتون لتقنية المعلومات جامعة موناش استراليا، له اهتمامات بحثية حول نظرية علوم الحاسب والمنطق الرياضي، تاريخ الرياضيات والأرقام خصوصا العربية، كما أن له أكثر من 150 منشور بما في ذلك 26 كتاب، 12 منهم تأليف و4 ترجمة و10 تحرير وأكثر من 100 ورقة بحث. سيحدثنا عن الخوارزمي في باريس نظرية الموسيقى. طبعا لا أعرف ارتباط الرياضيات بالموسيقى، ولكن سنستمتع إن شاء الله أيضا بحديثه عن الموسيقى، وسيكون موسيقيا. تفضل.
Thank you very much, Professor Aisha. I want to first just go back to one slide of Dr. Oates, which I want to talk about later, because that was a revelation to me. And there we go. Sorry about technicalities. Thank you very much. I apologize to the translator because I'll make a few remarks which are not in the text that I have. Some of this may seem a bit technical, but Professor Dean has copies of my talk, and I'm very happy for you to get a copy of it later and to read it or in bed or at other leisure time that you might have. First of all, thank you very much, Professor Dean, Professor Aisha, for the invitation to come here. My knowledge of the Arab and Islamic world is very limited, but the motto of my university is, I am still learning. That is very true. I have brought some things with me which I will try and remember to show to you at the end of this talk, and some of you may wish to talk to me privately afterwards, and I would be delighted if you would do so. Thank you all very much. The University of Paris was founded about 1215 in the Common Era. 594 after the Hijrah. The principal items of study included the trivium and the quadrivium. The trivium comprised logic, grammar and rhetoric, while the quadrivium comprised the mathematical sciences, arithmetic, geometry, astronomy and music. The quadrivium was very much relegated to a lower role. The Frenchman Beaujolin pointed out long ago that the mathematical subjects were only taught on feast days, of which there were many, and in Christian feast days, of course. It was not part of the regular course of study. Indeed, the newly felt influence of Aristotle, which of course had come through the Arab world, drove people away from mathematics. However, Rico has recently shown that there was much more teaching of and interest in mathematics than has previously been noted. The quadrivium, the mathematical part of the 7 arts, was traditionally divided into 2 parts: those concerned with number, namely arithmetic and music, and those compared with magnitude, sizes, geometry and astronomy. The distinction between number and magnitude goes back at least to Euclid. Magnitudes, length, area, weight, etc., have an obvious connection with geometry and astronomy. Quite literally, we see or feel the relation. Nowadays, it is hard to appreciate this difference. For us, lines, areas, volumes all have numerical sizes, and we compare them willy-nilly by using numbers. It was not so in the Middle Ages. The connection between was not so in the Middle Ages in Western Europe. The connection between arithmetic and music is more philosophical. Jacobus de España, who lived about from the 1260s to the 1330s of the Common Era, with whom I shall mainly be concerned, followed Boethius, who flourished about 500 of the Common Era, in other words 100 years before the Hijrah, and Pythagoras, the ancient Greek, all did not trust the senses, but required the theory of music to be in the domain of rules and reason. In Book 1, Chapter 9 of his classic work, De Institutione Musica, the discipline of music, Boethius said, "Not all judgment ought to be given to the senses, but reason ought more to be trusted. The ultimate perfection and the faculty of recognition consists in reason, which, holding itself to fixed rules, does not fall into any error." The basic point is that the senses are unreliable, while the Platonic world of mathematics is totally reliable. So to put music on a firm theoretical basis, it must be based on something intellectual, not on sensual experience. However, by about 1270 of the Common Era, 650 after the Hijrah, the works of Aristotle, newly rediscovered by Western Europeans, taught that sense data were the basis of all knowledge. This reflected a direct conflict between Platonic and Aristotelian ideals. The new approach made people in Western Europe change the way they were thinking. One consequence was they concentrated more on ontology, what things exist and their nature, rather than abstract theory. This in turn meant that the complicated mathematics that featured in the works of Boethius was, to a large extent, neglected. As I said, Boethius lived about 480 to 524 of Common Era, and mathematics in Western Europe hardly developed from his time until the Middle Ages. There was nothing like the sophisticated mathematics that was then found in the Middle East and the Far East. In turn, Boethius' work was based on that of Nicomachus, who lived around 100 of the Common Era, 500 years before the Hijrah, in Palestine. And Nicomachus was very definitely a Pythagorean. So the interest in these mathematical works was on the properties of numbers, for example, whether they were squares or cubes or primes, rather than on calculations of them. Calculations were largely left to the commercial sector, and that was where the work of Al-Khwarizmi had much more impact. Carrying out calculations was cumbrous, not because Roman numerals were used, because they weren't. Calculations were generally carried out in two ways. One was to use an abacus, and the other was to use ready reckoner tables, look up multiplications in those books, and then add up the results. Despite these difficulties, Boethius dealt with numbers as large as 500,000. It seems extremely likely that such large numbers were intimidating, and certainly doing the multiplications that Boethius did would have been very taxing. Very few people read beyond the first two books of his 5-book De Institutione Musica, and even there, almost entirely, they read them almost entirely for the ontological aspects. I said that before. They did, however, the people reading them did not, however, know the ratios that corresponded to the basic consonances, musical intervals in what is known as the Pythagorean scale, the scale which most Western music still uses. Basic examples are the octave. Is everybody familiar with piano keyboards and that sort of thing? So you know what they look like? Yes. Because I was thinking, that the music in the Arab world is working with different scales, the traditional Arabic music and so on. So there's the problems of cultural lack of knowledge on my part. Okay. So the consonances involve things like the octave, and that corresponds to a ratio of 2 to 1. The fourth, which corresponds to a ratio of 4 to 3. And when I talk about these ratios, I mean if you have a string and you make it half the length and then pluck it, the sound you'll get will be an octave higher. Okay? Carrying on. The fifth has a ratio of 3 to 2. The mathematics here is all very nice and neat. The tone, i.e. going along just one whole note, corresponds to 9 to 8. Incidentally, what one sees look like ratios, but the word ratio was rarely used in our present sense in the Middle Ages. Ratio meant reason or logic, ratio I should say. Proportions are merely represented by ratios. Thus 3 to 2 and 6 to 4 are in the same proportion. When we look at the usual Pythagorean scale and we start trying to add intervals together, say from middle C to F, and then which is a fourth, and then F to high C, which is a fifth, then we're adding a fourth and a fifth, and the corresponding proportions 4 to 3 and 3 to 2 are not added, but they're sort of multiplied. It's easier for us to think in terms of so-called vulgar fractions. There's the difficult calculation for you. So the whole interval from middle C to high C corresponds to 2 to 1. What a surprise, we knew it's 2 to 1 already. The trouble starts when we put an octave together from smaller intervals. Let's start again with the fifth, C to G, proportion 3 to 2. Now if we go to A, that's the tone, and the tone ratio is 9 to 8, so we now get 27 to 16. If we add another tone from A to B, we get another 9 to 8, and so we get 243 to 128. That leaves the semitone at the end from B to C, which we can regard as the octave minus that, minus the interval of the bottom part. Since adding intervals means multiplying proportions, subtracting means dividing. So for the semitone from B to C, we get 256 to 243. I think of this in terms of working out fractions and multiplying together, but that's anachronistic. Clearly, two of these semitones do not make a tone, at least as far as numbers are concerned. 256 times 256 divided by 243 times 243 is certainly not 9/8. Okay. Boethius called this semitone the minor semitone. If we look at the difference between this semitone and the whole tone, we get a different proportion. Namely 2187 to 2048. Don't worry about the numbers. The point is they're complicated, they're messy. Okay. Most of the people studying Boethius in the 13th century in Western Europe only got as far as the minor semitone. Ruceo, who was very much influenced by Aristotelian ideas and taught around 1270 of the Common Era, got as far as this semitone. His student Guy of Saint-Denis, writing about 1330, that should be, did likewise. Most people, however, got no further. There were two major exceptions. Excuse me. Jerome of Moravia, writing about 1270 in the Common Era, went through the whole of the 5 books of Boethius on music and included material that was needed from Boethius' book on arithmetic. Jerome may have come from Eastern Europe, but the accepted view is that he came from Moray in Scotland. The other person was Jacobus, and that's why I put this slide of oops, yeah, that one. Let's try again. Yeah. Jacobus was a friend of Jean de Meurre, whose book Jeff put up. And I didn't know that Jean de Meurre had worked on the Khwarizmis quadratic equations, so that was really nice to see today. So that's fine. And I'm trying to find my own. Oops. So this man Jacobus causes problems. Margaret Penn thinks he was Jacobus de España and came from Spain. Rob Wegman proposed he came from Liège in Belgium. Nevertheless, we do know he wrote the largest and most compendious book on the theory of music in the Middle Ages. We've only one complete manuscript of this. It's in Paris. I call it Paris 7207. It's huge. It's more than 600 pages, comprising 6 books. This is just a list of the chapters in the first book, right at the very beginning. There are 2 other manuscripts, but they're incomplete. There's a second one in Paris and the third in Italy. Jacobus himself records that he heard lectures on the first 2 books of the Boethian De Institutione Musica in Paris, probably in the late 1290s. It's clear, however, that Jacobus ultimately read all 5 books. Someone kindly lent him a copy of Boethius. So, the work of Jacobus certainly contains all of the knowledge of Boethius, and like Jerome of Moray, he includes whatever is necessary from the arithmetic of Boethius. However, his aim was higher. He wanted to produce the most complete encyclopedia of the theory of music that he could. He set out to provide a clear and exhaustive, some would say exhausting, account of the Boethian theory of music. His aim is clear from the title, Speculum Musicae, the mirror of music. That speculum was the standard term used at that time to indicate such an all-embracing treatise. Despite his persistence, Jacobus found the mathematics of Boethius hard to understand, and he states this quite firmly at the very beginning. but the work that I took on was laborious and long for me, and many cogitations had to be expended, and it was begun too late in my life. At that time, Arab science was only slowly making its way into Europe. Though the Arabs from North Africa had been in Spain since the 8th century on the Christian era, 200 years after the Hijrah. In Toledo, Spain, the three peoples of the book, Christians, Muslims and Jews, lived in convivencia, a relatively stable and peaceful mix. Men from England and Italy worked with the people there, producing translations from Arabic of fundamental scientific works, as Jeff has already mentioned. Among these were the works of Euclid and, of course, of Khwarizmi. Slowly, very slowly, knowledge of this work spread northwards. In particular, the arithmetic of Khwarizmi was propagated in two relatively popular works, though it seems that the Latin version of his text was considered hard and technical. In Western Europe, the techniques of Khwarizmi became known as the art of algorithm, a sort of Latin version of his name. The art of algorithm comprises how to write and read Hindu-Arabic numerals and the methods of doing arithmetical computations with them, which we've heard about from our two previous speakers. As I've shown elsewhere, the Hindu-Arabic numerals were only very slowly taken up in the West. The methods of calculating, in particular multiplying, were much simpler once was used to operating with, or even just reading, the numerals. Another distinguishing feature of algorithms is the way that calculations, addition, subtraction, multiplication and division are made. When one works with an abacus, no trace remains of the steps in the calculations once it is complete. By contrast, using Arabic numerals on paper or even on a wax tablet, the techniques of algorithm leave traces that can be independently verified. One can check the working. This also reduces the chance of error. This newly introduced, though ancient way of doing arithmetic made a great difference. Jacobus only mentions algorithm on two occasions. First, he commends Robert Kilwardby, an English scholar whom Jacobus may have met or even studied with in Oxford. Kilwardby includes algorithm as a practical art, extending the traditional Boethian theory of music in his book, The Origin of the Sciences. On the second occasion, Jacobus revels in the value of arithmetic and shows great enthusiasm for the advantages of algorithm. He said, "Oh, how useful is the science of algorithm." His knowledge of algorithm surely made an enormous difference to him in doing his calculations, and it indeed was what made his books 2 and 3 as possible. As I said earlier, working with Roman numerals was, to say the least, cumbrous. However, the new Hindu-Arabic numerals were treated as being different from ordinary letters and Roman numerals. Numbers in the Paris 7207 manuscript are represented in 3 different ways: Roman numerals, Latin words, and Arabic numerals. Although this manuscript was prepared over 100 years after Jacobus first wrote his text, it seems to me that the Hindu-Arabic numerals reflect the work of Jacobus himself. There are several reasons to believe that the original text used the same various representations of numbers. The first 2 types of notation, Roman numerals and Latin words, require no explanation. However, all 3 forms are used from very on in the work. Then at the end of Book 2, Chapter 49, Folio 59, verse so, there is this text, which translates as, "Therefore the comma," which is a tiny musical interval, "stands in the super 7153 partiad proportion of 524,288 parts in numbers." Don't worry about the numbers. They're large, they're complicated, but Jacobus knew what he was doing. The word partiente is inserted below the quingenta here, and the Roman numeral 24 is at the end of the line. The text in the other Paris manuscript is virtually identical, the only difference being that the partiente is missing. If the scribe was not slavishly following the text, surely he would have used Arabic numerals to take up less space. Moreover, the other copies doesn't seem to understand what he was copying, since this word partiente at the bottom is needed, but he didn't actually include it. In both cases, they used Roman numerals. I therefore believe they were copying from the same earlier manuscript. Remember, our manuscripts are from a century after the text was written by Jacobus. Further, Jacobus' enthusiasm for algorithm would have led him to favour Arabic numerals over Roman ones, at least for large numbers. So I believe that the numerals that Jacobus used were as they are in his manuscripts. And there are very many of them. In general, only small numbers, say below 100, are not written in Arabic numerals. Exactly how Jacobus acquired his knowledge of Arabic numerals and algorithm we do not know. Now I mentioned about Jean de Meur, but Jean de Meur was a later friend whom we made only, I think, after he'd written this speculum, so I don't think he got it from him. However, there were people in Paris, even before 1300, who knew about algorithm. That is not to say it was widely known. It is unknown what number or fraction of people taught or knew such matter. On the other hand, it seems very likely that those few knowledgeable in this new mathematics should know each other. Jacobus used his knowledge of algorithm to revive, and not merely revise or rework, and extend the work of Boethius. I've written elsewhere on an old puzzle, what is half a tone, but here I would like to give an example directly from the manuscript of the large calculations of Jacobus. And like Jeff, you don't have to read it all, just see that it is complicated to do. Jacobus gives a list of the 51 musical intervals he considers at the end of his book too. Here's just one, but it involves the largest numbers. He calculates the proportions for a major tone, which is 2 major semitones, or above, or alternatively a tone minus a minor semitone. Okay. So, sorry, I got that wrong there. The major tone is 2 major semitones. A major semitone is a tone minus a minor semitone. A minor semitone is this proportion. So what it all comes down to is this ratio with 4 million and something to 4 million and something else. There's more. Jacobus proved that this ratio is greater than 9 to 8 and less than 87. The modern calculator would simply express these as ratios using decimal fractions, but decimal fractions were not invented until 200 years later by Simon Stevin. And then people would just compare them, but the proof Jacobus gives for the former is remarkably simple. He simply compares the differentiae, i.e. the difference in the number of parts. So you take these two large numbers and look at their difference, which is 5, 8, 8, 6, 6, 5, and for 9 and 8 it is 1. Division is not an option for Jacobus, since he's already dealing with fractions. So instead, he looks at the size of this number relative to the whole and compares this with 1/9. We would say he scales matters up. Oh, so that explains right. Sorry. So, I won't go into the technicalities anymore at this point. It is in my text. But it then eventually shows that the first number of the proportion for the major tone lies between the two numbers we've been talking about, and so the proportion is less than 8 to 7 and greater than 9 to 8. Jacobus presented as full a picture of Boethian music theory as was possible at the time. His aim was fulfilled, but not without effort. At the end of book 3, he explains how he reiterates how he had to think very hard and do many calculations, but it had also been fun. If I have been lacking, it's because I am not sufficient to fully understand such hard material, which requires many cogitations and many operations with numbers. But then he continues, if they, meaning the readers, are lovers of music theory, they will delight in it. They will revel in the proportions of numbers, in the varieties and stupendous comparisons of huge numbers. He's come a long way. He has revisited, revived and expanded the work of Boethius, defending him and the supremacy of intellect over sense. He has clung tightly to the Pythagorean tradition while being aware of and accommodating the new ideas of Aristotle. His desire to thoroughly understand the work of Boethius has been made easier by his knowledge of the new science of the algorithm. Indeed, that useful science has made it possible for him to handle numbers an order of magnitude larger than those in Boethius. And it almost certainly made the calculations much easier than using Roman numerals and more reliable than using an abacus. His aim was to present a comprehensive treatment of the theory of music, something that had not been done previously. He did that, reviving interest in the work of Boethius, taking into account newly rediscovered ideas of Aristotle and incorporating the necessary mathematics, so that the union of mathematics and music theory will be available in one grand, truly encyclopedic source. In doing that, he went beyond Boethius because he could use the techniques of Khwarizmi. This master not only affected the development of arithmetic and algebra in Western Europe, but also the theory of music of that period. Later, his name will be preserved in the theory of algorithms, as well as algorithm, but that's another story and a different part of my life. Thank you. Can I just, as I promised, I brought two books with me, which you might like to look at. It was only after I'd done the work on Khwarizmi that Folkert discovered manuscript in New York with the full text of the arithmetic of Khwarizmi. This is the Latin edition. We don't have any Arabic version. And in the 19th century, Rosen did an edition of the algebra, which is complete with pictures, which has been published, was being fairly recently republished, so that's available. And I didn't know how many of you had actually seen, so to say, the actual work of Khwarizmi. So if you'd like to look at these afterwards, I'll be delighted. And as I said before, I'm grateful to you for coming. I'm especially moved by the lovely smiles I'm getting at the moment. So thank you very much.
شكرا جزيلا، لأن الابتسامات هي أيضا موسيقى، يعني الابتسامات تمثل الموسيقى، فشكرا جزيلا، موسيقى إنسانية. شكرا جزيلا الأستاذ الدكتور جون كروسلي، وشكرا أيضا للكتابين ممكن أن يتبناهما مركز محمد بن حمد الثاني لإصابة المسلمين في الحضارة، فيترجم ما يعني لم يترجم ويحقق ما هو مترجم إن شاء الله. شكرا جزيلا. نفتح المجال للمناقشة، من يحب أن يداخل أو لديه تعليق تفضلي. عرفي بس باسمك.
My name is Noor. My name is Noor. I did my bachelor's in math at MIT, and now I'm a master's student here at QFIS studying contemporary Muslim thought. Thank you very much for all of your presentations. I think there was like one or two references made to the motivation behind Khwarizmi's work in math. So I think Dr. Tamadar, you mentioned that he did use it for inheritance in fiqh. I think maybe Professor Jeffrey, you also maybe alluded to the motivations behind can we speak more to what really drove his work? Did he include an introduction to his works where he explicitly, said, I'm doing this is it for the advancement of knowledge, just in general, in abstract terms, or is it specifically for use for finding the Qibla or doing inheritance, or?
Yes, fortunately, he does have an introduction to his algebra book. And he says that he was asked to write a book on algebra by the Caliph Al-Mamun. He was asked, and asked not just to write the book, but to write it specifically for the people who use the calculations in their jobs. He mentions diggers of canals, people who work on inheritance, people who work on various trades. I can't remember exactly how the quotation goes, but he is explicitly stated it's for practical purposes. But then when you read the book, you can tell that he's also kind of thinking in a theoretical direction. He kind of takes it in that direction.
May I just add to that? From the beginning of the algebra book, when I considered what people generally want in calculating, I found that it always is a number.
Assalamu alaikum, Dr. Abdul Wahid Hamdi from Qatar University. I'm doing mathematics. So for Professor Jeffrey, please, today when we are teaching to our students, we said the discriminant. When we have ax squared plus bx plus equal to 0, so how to solve them? We write down first the discriminant, b squared minus 4ac. So did Khwarizmi gave this, or who proposed these things?
Okay, Al-Khwarizmi gives a numerical rule for solving the equations. So I'll just give you an example. I don't know if you can follow this in your head, but I'll give you one. X squared plus 10x equals 39. This is the example he gives in his book, stated rhetorically, of course. So the rule is you take half the number of roots, which means take half of the 10. You multiply it by itself. Then you add it to the number. That will give you the discriminant. And then he says, then take the root of the result. Take the square root of the result, and then subtract from it half the number of the 10, and you have your answer. Now, it's not exactly the same form. It's equivalent to the formula we give them today, but he does calculate the discriminant that way as a numerical rule. And Diophantus did the same thing in his book, but he did it in a slightly different form. So yeah, he does give the rule. And he's not worried about whether or not the number is irrational. Because for Al-Khwarizmi, numbers can be integers, they can be fractions, they can be irrational. There's no problem at all for them. They just can't be negative or zero. Those were forbidden.
This is Muhammad Mudathir Ali. Mathematics is totally Greek to me. So I'm coming from a very lay background. I just wanted to ask Dr. Tamardo, she said that Khwarizmi used digits as numerals, if I got that right. I wanted to know what that means. I mean, what is the difference between digits and numerals? And Professor Jeffrey, you said that the Arabs, the oral tradition of the Arabs, they could actually count on both hands from 1 to 999? If I got that wrong, please could you explain? And thank you very much, the whole panel, for the wonderful lecture. Thanks a lot.
From my understanding, I just want to explain. When I say digit, it means the number from 0 to 9. So this is what I mean by digits. But then they were used as numbers to make 1,000, 9,230 something, and written together, unlike the Roman numerals and unlike other methods of writing the number.
Okay, what they didn't actually count on their fingers. Let's say you wanted to multiply 43 by 87 in your head. Now you can probably do 43 by the 7 of the 87 and get a partial result. And there were ways of positioning, maybe touching the index finger to the palm and moving the thumb one way to store a number on one hand and then the rest of the number here. You could position your fingers in such a way that it represents a number between 1 and 9,999. So you store that number, then you do the other calculation by multiplying by the tens, and you get a result that you have to add to this. So if you were to try to do it all in your head without storing the numbers, you forget what the first number is. That's what I mean by that. So you didn't actually count on your fingers, you stored numbers on your fingers. So it was all done, and they liked doing this because they didn't like writing the numbers down. If you're in the market negotiating with someone, you don't want to write down the numbers so they can see. That's one of the reasons for doing it mentally.
If you want to see diagrams of the contortions with the fingers, then the English monk Bede lived about 500 of the Common Era. You'll find them very easily on the web. Just BEDE finger counting, and it will bring it up.
Yeah. There's a medieval Arabic poem which explains how to position the fingers for the different numbers. I have a text of that, and there are illustrations in some European books. Fibonacci's Liber Abaci that I mentioned has a diagram showing how all the fingers are, because this method was used throughout the entire old world. It wasn't just in the Arabic lands.
Oh, no, yes. First of all, thank you for this interesting, lecture. And I have two questions. Number one, the movement, the medieval movement of translation from Latin, from Arabic into Latin. A number of works were translated without mentioning the name of the authors. And my question is, how large was this phenomenon, and what is its impact on the history of science, like history of mathematics here? Yes, the other question is about the importance of Arabic as a language of science in the medieval period. And maybe its failure, to be a language of science in the modern period. What comment maybe you have on this? Thank you.
Okay, I can answer the first question, which is that the texts I read do give the name of the Arabic authors. They do. Al-Khwarizmi's name is mentioned in the Latin translations, except the third translation doesn't have it. But that third translation, presumably by Guillaume de Lunis, was not studied much. But Robertson and Gerard's translations did contain the name at the top. And it was also in the medieval Latin translations of the arithmetic. Al-Khwarizmi's name was included there also. And I haven't studied the medieval Latin text in enough detail to pay attention to whose name is mentioned and whose isn't. So I've really focused on algebra, so I can't say any more than that. I believe Abu Kamil's name is attached to his translation. What I find in the texts I read is that the names disappear when someone is adapting someone's work in their own work. And that's when I find the name disappearing. Although Fibonacci does have, he has in the margin of his Liber Abaci just the name Muhammad for Al-Khwarizmi, but without explaining why it's in the margin. So it's not, they're not trying to deny any origin, it's just not important because they're just producing a mathematics work. Now, can you repeat your second question?
With regard to the position of Arabic as a language of science.
Oh. Yeah, Arabic, this isn't something I've studied in any detail. All I can tell you is that Arabic as a language of science it developed in this sense. I would say, from what I've read, this is not my area of research, but what I understand from what I've read is that Arabic was not really a language well suited for science in the 7th century or the 8th century, but that the language itself developed to accommodate science during the translation movement. And then by the end of the translation movement, it was an excellent language for transmitting science. Certain linguistic innovations were developed for Arabic that made it such. And then I've heard many people claim that a certain language is good for a certain kind of thought. I've heard people say that German and Greek are the best languages for philosophy, but I don't really hold to these views very well. Arabic was a wonderful language for philosophy as well, as anyone knows who's studied Ibn Sina or any of the Arabic tradition. And the people who translated these into Latin understood that very well.
on the translation, the general practice in the medieval ages in the West was, even for authors quoting other authors, that they didn't put the names in. They put in the names of classical authors, though Aristotle's usually referred to as the philosopher. And so there was a general omission of names. And I don't know whether it was because they were assuming that their readers would know who these texts were coming from. I have colleagues who've been using what I call computer plagiarism detection methods for finding out where text came from. And they've completely reversed the ideas about one of these encyclopedias as the Speculum Morale. So there's a lot of work to be done on that, and we've only just been able to do it. In terms of your second question about the language of Arabic, you can tell how ignorant I am. I hadn't realized until I heard Jeff's talk today that astrolabe is an Arabic word. And I saw it written there. My Arabic reading is very, very poor. But I could read that it said astrolabe in Arabic. So, and all those words are around us. I mean, chemistry and all sorts of things, food names in particular that we come. So there's the question of the words and the language. And if you look at mathematics in Russian in the mid-20th century, what they did was they took Western names in a lot of cases and just made them into Russian names. So the Russian for group is groupie, you know. So there's this question of when you're dealing with new concepts, you may not have a word in the language, in your own language, that corresponds for one word in the other language. And people like Gerard of Cremona were trying to do word-for-word translations. And in the Latin translations I've done, I've tried to do the same. But every now and again you get stuck. And we were thrown on one of the other music, I mentioned the name Brocheo, he had another music treatise. And he talked about the Alps. And we didn't know what it meant. There was a mistranscription in the edition that was available. Anyhow, I talked to my friend Charles Burnett, who's a great scholar of medieval Arabic period. And he said, oh, that's I think it's the perihelion. When you've got the planet going around the sun, then I think the perihelion is the Alps. But there were other things where Gerard had to make paraphrases because he couldn't have, there wasn't a single word for that thing. So.
Assalamu alaikum wa rahmatullahi wa barakatuh. My name is Fatih Ahmed. And first of all, I would like to thank our distinguished speakers for these wonderful presentations. I really enjoyed it much, though I'm not of mathematics background, but I really appreciate your time and efforts in enlightening us with these wonderful presentations. I think one of the questions that I would like to ask our distinguished speakers, to what extent you are really sharing this knowledge about Al-Khwarizmi and the like of other Muslims or non-Muslims to your students, whether in the States or in Qatar University or in Australia. It's very important because to contribute and because knowledge has definitely no nation and no country. This is number one. Number two, my question is directly now to Professor Jeffrey. You did some efforts to work out what are the original contributions of Al-Khwarizmi and what are the non-original one. So what I would like to know is what's your methodology and how did you find out this to make sure that your findings are really, clear and convincing. Thank you.
Okay. I teach mathematics, so I normally teach calculus or algebra and trigonometry or higher level mathematics. So the history would not normally come into play, but I always tell them about my research. So they all know that I'm studying medieval Arabic mathematics, and I make sure they understand something about chronology and in history and geography, because most of them really are, at least in mathematics, they're kind of deficient in that area, let's say. So my students do know about medieval Arabic algebra. They know algebra comes from Arabic, the word comes from Arabic, that our whole tradition comes from Arabic. So, as for the second question, it's a very difficult question. And I'm fairly confident, I'll explain this in a second, I'm fairly confident that the way that this worked out problems are phrased was Al-Khwarizmi's development, and the classification of 6 equations, I'm quite sure that was his development, and the proofs too. And here, I guess I'll briefly explain I wrote an article about this that I published in 2012, because it's kind of a technical argument using internal linguistic cues. If you look at the work, starting with the worked out problems, he'll have 6 problems that are framed in very explicit terms, very nicely and easy to understand. Then come 33 or 34 other problems. And what's curious is that 11 of those problems are not solved by algebra. They're solved by some other more primitive technique of just sort of reasoning through the problem. There's no name that's unknown, no equation is set up or solved. So it would be kind of curious for someone who is, let's say developing algebra to include these problems as well. So what I find from this is that the second group of problems, the larger group, are problems that he probably just took from some oral source or maybe even some earlier written source. These are not, and what he did was he reworked them into the 6 problems. So that there's that aspect of it. And once you see that he's reworked 6 problems, then the classification, this is kind of by association. I don't really know for sure. What I put up there was a guess. It's a reasonable guess, but once we have 6 problems identified by Al-Khwarizmi, then it's only natural to suppose that he classified those 6 problems. Also, Diophantus did not classify 6 problems. And since he didn't, that's just a tiny bit more evidence that it is Al-Khwarizmi's own idea. So really, it is a very, very difficult question, and there's no doubt that Al-Khwarizmi did make significant contributions to algebra in his book, but since he doesn't tell us what they were, we just have to use these linguistic cues to make guesses.
I'll leave that question to Jeff, but the question of sharing knowledge. I not only work on medieval music theory, I also work on the early colonial Philippines around about 1600. What's been very striking to me over recent years has been a shift in attitude, even among scholars, Atlantic scholars, scholars from Western Europe and the United States, taking into account what was happening in China, what was happening in the Arab world in those periods. Indeed, the question, an interesting simple question has been raised, should we talk about medieval when we've got Song and Tang and Yuan dynasties in China, and of course you've got Hijra in the Middle East. So there's a shift in the language, and there's a shift in the interest. And there's a book that came out in the 1990s, I think, or even earlier, called Asia in the Making of Europe, which I think was one of the earliest books to take into account the interactions which had been going on for centuries in trade. And the Arab world was the center of that, because the soldiers were coming through from China into Western Europe. So there was interaction, but we in the West have concentrated on the Latin West, and that's been bad. And then in very practical terms, in the 70s and the 80s, the history of mathematics was quite popular in my university. It's gone into decline, I don't know why. Interest in other parts seems to have gone up and down, but when people are studying history of mathematics, then the Arab world is just so important. And then also in practical terms, on Friday mornings, I usually spend the morning with a group called the Center for Medieval and Renaissance Studies, or Renaissance Studies at Monash, which has now grown to more than 20 people. We study Latin text. We had a talk on the first ghettos for the Jews in Rome in the 16th century, just in the last week or two. We've got a new appointment of a Turkish guy who's working on Islamic and Jewish studies and so on. So the university is getting more aware of these things. And I'm hoping to do some talking while I'm here, because we have a Centre for Theological Studies, which is very much concerned with the three religions of the book. And so we are hoping to develop further dialogue. We have an awful lot of Lebanese in particular, but a significant number of Arab speakers in Australia. You probably heard unfavourable comments in the press about some of our politicians and what they've been saying about Islam. Not as bad as the US, I don't think, but I think pretty bad. And that's shocking to me and to very many of my friends, some of whom know nothing much about Islam at all. I think that the education has to develop. I think there are more people getting involved in it, and that's better. And when I come to Doha, and I come through immigration, the official there, I don't think he said peace, but he said welcome, and it was sincere. Thank you. Now, one question. Do you mind if I take your photograph? You can take it out. Anybody object? Yes. Thank you. Thank you very much.
I just want to answer the last question. I'm just starting in this, but I'm planning to do another talk on the same topic at Qatar University, and the students should be invited to that talk. And hopefully we can try to get them to know these things better. Maybe we can have posters and stuff, because we are launching a new program in mathematics, and we're trying to get people to know more about mathematics. And I think this knowing about the Arab scientists or Muslim scientists will help them get some motivation a little bit for the students. And also, I think that's it. Thank you.
I just wanted to add briefly that we have a number of students from Saudi Arabia at my university, and I always have 3 or 4 in my classes, and they're always very excited when I mention the medieval algebra. They come to my office and we talk, and I show them the medieval texts, and they're all excited and wonder how in the world I can read these handwritten things from the 1200s. I can't read the newspaper, but I can read the manuscripts. So, yes.
شكرا جزيلا. أعتقد يعني استمتعنا جدا حقيقة بهذه الندوة طبعا التي تظهر جانب من جوانب إسهامات المسلمين في الحضارة. فشكرا للدكتورة تماضر خليفة العسيري، وشكرا للأستاذ الدكتور جيفري أوكاس والأستاذ الدكتور جون كروسلي، وشكرا لكم جميعا ولمداخلاتكم ولاستماعكم ولابتساماتكم كما يقول الأخ الكريم. فشكرا جزيلا، وإن شاء الله نلتقي على خير إن شاء الله. تفضلوا. شكرا جزيلا.